Okay, yeah. So it's okay. Hello everyone. Welcome to the mini course in Finite Geometry and Ramsey Theory. I'm Anurag, and in this course, I try to give you a glimpse of some recent developments that have happened in this area called Ramsey Theory, where the main tools that have been used come from an area that I am more of an expert in, finite geometry. So that's my background. But I'm starting to get into Ramsey theory as well. And there's this course website. I hope you have seen it. I'll be posting the lecture notes there every week. Well, every day. It's every day, and you'll see more details in the lecture notes there than compared to the what I'll be presenting to you. So I'll leave some of the proofs of, especially from the background stuff from the basic theory, and just give you a rough sketch, but you can see all the proofs and the details there. Okay, so let's just begin with the maths. So this course is about two topics basically and their interplay. One of them is finite geometry, which maybe some of you are maybe experts in, and some of you have no idea about what this is. But it's essentially the study of geometric structures. So you have finite structures. I'll define what they are, but they always satisfy some sort of a geometric axiom. So for example, we'll see things like projective spaces or even affine spaces. If you know what they are, you don't have to, I'll introduce what these things are, but we will be seeing finite versions of these geometric objects. So that's essentially the study of finite geometry. You look at these classical geometric objects and you make them finite and see what happens. And Ramsey theory is, again, some of you who are from the more finite geometry background, maybe you don't know what this is, but I see a lot of combinatorics people and experts in the area who, of course, know what Ramsey theory is. But instead of going by the cliched line of, about the chaos and whatever, so this is my summary of it, that it's a study of unavoidable substructures in partitions of large enough structure. So whenever you have some mathematical object and you partition it, which in Ramsey theory is often stated as coloring something there, and then those color classes are your partitions, then if your structure is large enough, uh, at least one of the color class will have some fixed structure. That's the basic idea of Ramsey theory. And the classical thing, which we will be working on, is graph Ramsey theory. So here, the quintessential example that many of you might have, you would know, that if you have a group of 6 people, then at least 3 of them would either be friends or 3 of them would be strangers. This is the classical graph Ramsey theory result, and we'll build up on that and introduce what these things are and what Ramsey numbers are and see some bounds on that. Okay, so here's the quick outline. This will be a 2-week course. We will have 6 lectures, and all the lectures will be recorded and later posted on YouTube. I'll send you all a link later on. Then there will be 2 exercise sessions. These correspond to the first 4 lectures. So after the first 2 lectures, we have an exercise session, then again after the next 2, because the first 4 lectures really focus more on the background and the theory. And the last 2 lectures are about the new developments that have happened in Ramsey theory. So the last 2 lectures then would naturally lead to 2 open problem sessions, which will be next Thursday and Friday. And we'll probably give you more details on that, but roughly think of some nice open problems which you think would fit the realm of this course, and suggest them to me, and we will compile them. And then in the last 2 days, we will try to discuss some of those open problems and maybe break into small groups to think about some ideas and brainstorm. That's the rough idea. Okay, so that's it about the introduction. Let's just jump straight into the maths here. And the basic object that we will see in our course in the finite geometrical world is the notion of a point line geometry. So this is just a triple of sets where the first set is often referred to as the point set, L is referred to as the line set. And this last thing is just an incidence relation. So it's just a relation between points and lines. So it's a subset of P cross L, such that we have this non-triviality condition, which says every line is incident to at least 2 points. So there is some sort of a distinction between what lines are and what points are, right? Because each line has at least 2 points. You can't identify lines by points. That's essentially what we want. It's a very, very broad concept, and we will focus on a specific kind of point line geometries, which are known as partial linear spaces. And they have this condition that if you take any 2 points, so any 2 elements of the first set P, then there is at most one line through them. So at most one line incident with them. Okay. And for those of you who are more familiar with graph theory and combinatorics, this is exactly equivalent to linear hypergraphs. If you know what those are, maybe that's a very strange writing. But anyway, linear hypergraphs. If you know what those are, if you don't know, it's okay. Just think of these as you're just seeing this definition. These are the objects you'll be concerned with. But linear hypergraphs are basically partial linear spaces. And the idea is that with each line, you can identify it with the subset of points it's incident to. And that becomes your hyperedge. And that's how you get the hypergraph. Okay, quick examples. Well, just a trivial looking thing, maybe. This simple graph is a point line geometry. The vertices are my points and the edges are my lines. Okay. In fact, any simple graph, or in fact even multigraph without loops, is a point line geometry. And any simple graph is a partial linear space, because between two vertices you have at most one edge. But what we are more interested in are the geometric examples. So what motivates these definitions? And for that, let's just look at the Euclidean plane. So your P is R squared, and your line set is all lines, right? So the Euclidean, the affine lines, let's say. So all lines in the plane and all points of the plane. You define incidence naturally as containment. This is, of course, this should be a point line geometry if we are calling something a point line geometry, right? It will be very strange if these classical things are not point line geometries. All the objects we will see will be partial linear spaces, and but it's still a good idea to have this definition with the incidence relation in mind, because you will see later on in the course there'll be some weird looking geometries which will be defined by crazy incidences between different sort of things. So it's a good idea to have that incidence model in mind instead of just the linear hypergraph model. Okay, maybe just aesthetically. All right, so now we are ready to jump in the first example of our partial linear space. So this is an affine plane. It's the object that you get when you just look at the incidence properties of your Euclidean plane and abstract that out. So here you have a partial linear space. Oh, well, okay, important thing. You have a linear space here. I did not define what that was. So a linear space, why is it called a partial linear space is because a linear space is just a point line geometry where there exists a unique L through any 2 points, X and Y. So instead of at most one, you have exactly one line through every pair of points. Then that's called a linear space. So this is a linear space. Okay. So an affine plane is just a linear space. So partial linear space with that extra thing, with these two geometric axioms, or at least the first one looks like a geometric axiom, which says, let me draw this here. So it says that if you take a point in your point line geometry and you take a line, which does not contain this point, so it's not incident with this point, then, so say this is P and this is L, then it says there exists a unique line M passing through P, which is disjoint from L, in the sense that they don't have any common points which are incident to them. Okay, so this sort of is the parallel axiom in the Euclidean geometry, right? So you just keep this parallel axiom and you keep the second thing, which is just a non-degeneracy condition that just says there exists at least 3 points in your geometry looking like this, so that they don't all lie on a common line. So this ensures that you don't have a trivial structure like just a line with a bunch of points on them. Right? That will be a trivial example of an affine plane because the first axiom is vacuously true. Okay, and that's it. So if you just define your structure using these two axioms, quite surprisingly, you get a very rich structure. And of course, as I said, we are abstracting out the definition of the real plane. So I will denote the Euclidean affine plane by this notation, AG2, R. This is affine geometry, dimension 2, and this is your field R. Here the points are R squared, so the Euclidean plane, and lines are all the lines of your Euclidean plane. Of course, you can do the same thing over any arbitrary field, F. And that's where we realized that this could be finite. Right? So there could be a finite affine plane by just plugging in a finite field there. And I will denote this finite affine plane over the finite field FQ by AG2, Q, where Q is a prime power. Okay. Yeah, I should say that if you have any questions whatsoever, post them in the chat or unmute yourself and ask me. There are these experts in finite geometry here who can answer your finite geometry questions. There are these experts in Ramsey theory who can answer your Ramsey theory questions. So my job is really easy here. Okay. This will be our main example, AG2, Q, or these sort of examples which work over finite field. You just plug in a finite field inside something and you get your finite geometry. What else? Maybe I can just quickly draw one of them. So this thing here, oops. This is, if you have your binary field F2, then this is your affine plane over F2, AG of 2, 2. Okay. There are many more examples. I won't be covering them. So it makes sense to study this abstract structure because it's not just going to be these examples. We don't need it for this course for applications to Ramsey theory, but I'll write about them maybe in the lecture notes. Okay, so as I said, just from these, give me a second. Sorry. So as I said, just starting from these axioms, you can actually derive a lot of structure. And one of the first things you observe from these axioms is that you can define an equivalence relation on the lines of your affine plane. So whenever you have an affine plane, you just look at this relation, which we call parallelism. So let's write it here. You can define this notion of parallelism where it's a relation between two lines whenever they are either equal or disjoint from each other. So they don't have a common point incident to each other. And from the axioms, you can show that this thing is an equivalence relation. So it actually partitions all the lines of your affine plane. And this is an abstract affine plane. We are not just looking at the AG2, Fs, but anything. Why don't we have, okay, there's a question. Yeah, so good point. You can think of it as just subsets of points, but later on in the course, I'll give you some definitions of finite geometries where it's really messy to write down your lines as subsets of points. It's much better to have incidence relations described between these weird looking objects. And I think so that's the main reason for you to at least get comfortable with it. But for now, just imagine your lines as subsets of points. That's perfectly fine. There's nothing, especially for a partial linear space, that's okay. All right, so quickly I'll sketch, I think it's only conceptual. Yeah, definitely. It's a conceptual list. Okay, so for the equivalence relation, it's straightforward from the, some of the properties are straightforward from the disjointness, this thing that it's reflexive and it's symmetric. But for transitive, maybe you have to think a little bit. So if you have two lines or three lines, let's draw three lines. So say L, M, and N, such that L is parallel to M, M is parallel to N, then you have to show that L is also parallel to N. And say this wasn't the case, say somewhere down here, they did meet, then you will run into a problem, and let's see what the problem would be. So you'll hopefully negate the first axiom, because through this point P, and which does not lie on the line M, there are two lines which are parallel to M. So that negates the first axiom, all right? So that's why it's an equivalence relation, and that helps us a lot. In fact, if you add the extra assumption, which is the assumption we will mostly be working with, that your affine plane is finite. So if you add finiteness, then you can show the following. You can derive this sort of structure which says that for every finite affine plane, there exists a positive integer, at least two. This is known as the order of the affine plane, such that every line has exactly n points on it. So all lines have the same number of points. Through every point, there are n plus 1 lines. So it's again a constant. And then every parallel class, so equivalence class of this relation, the parallelism, each of them has exactly n lines. So there are n lines in each parallel class. There are in total n plus 1 parallel classes. You can find out the total number of points, which is n squared, and then the total number of lines as well, in terms of this one parameter n, right? It's a very fascinating thing that just from those two axioms, you could derive so much. And instead of proving all of this, so that you can also have some fun playing around with these axioms, I'll just quickly sketch the second one, maybe. Okay, so here's the idea. Say you have 2 points, x and y, and if you take any line through y, then from the first axiom, if you remember the first axiom of the affine plane, there is a unique line through x which is parallel to y, so which is disjoint from y, right? And that just gives you a bijection between all lines incident to y and lines incident to x. So this way you get a bijection. Now you call the number, this constant number of lines through each point as n plus 1. And then you can prove that each line has endpoints and all the other claims as well. Okay, and this will be a fun exercise for you too. If you're seeing this for the first time, it's nice to derive all of these things. So for example, in AG2, Q, n is q. So there are q square points, which you all knew, of course. This is fq squared. And there are q square plus q lines. These are all lines of the form y equal to mx plus c and x equal to c. Okay, and you can count them, you get q square plus q lines. This is a main example. All right, so that's your quick introduction to finite affine planes. We won't really need these geometries later on so much, but it's a good place to start because it's something you're already familiar with, the Euclidean plane. What we will mostly focus on is something known as a projective plane, and in general, projective geometry, because that really allows us to define many more interesting finite geometry objects which have applications. I mean, given n, does there exist? No, that's a very good question. And in fact, that's a big, big open problem. That what are all the affine planes? In fact, all the examples that we know for affine planes have n a power of prime. So there are many weird looking examples. They don't come from AG2 comma Q. You can modify this plane and you can do many more things. There are actually I think asymptotically, there are super polynomial many non-isomorphic examples. So there are many examples for sure. Well, maybe yeah, I think I'm right. Anyway, but all of them end up having n a power of prime. And this is known as the prime power conjecture. Whether all of these affine planes actually have prime power conjugate. Can you construct an affine plane of a non-prime power order? That has been open for past, I don't know, 70, 80 years or something like that. We have absolutely no idea. We have some results which rule out a lot of infinite families of non-prime powers, but in general, it's a very terribly hard open problem. Okay. Any more questions with affine planes? Just give me a second. Sorry, okay. Yeah, let's move on to the main partial linear space, or the main finite geometry that will concern us. It's the so-called projective plane. So again, you can define it very easily with just two axioms. It's a linear space such that for every pair of lines, there is at least one point incident to both of them. So the intersection is non-empty. I'm abusing the notation here, as someone mentioned that we can think of lines as subsets of points. And then there's this non-degeneracy condition that there are these 4 points such that no 3 of them are collinear. That's what this means. So there are at least these 4 points in general position, let's say. Okay. And the sort of beautiful thing about projective planes, and also the reason why they become super useful, not just in finite geometry, combinatorics, and so on, but also in algebraic geometry, where if you have some background in algebraic geometry, you would have definitely seen projective planes. But judging by the fact that this is a combinatorics audience, maybe yeah, we don't really see algebraic geometry that much. Okay, so there is this really beautiful thing called duality, which says that if you just replace your points and lines, so your points becomes lines, your lines become points, even then you end up with a projective plane, because these axioms are sort of dual. And why is that? Well, recall that in a linear space, you have a unique line through any pair of points, right? And this condition, in fact, says that for any pair of lines, there is a unique point. In fact, you can show that this is the case. Because if two lines meet in more than one point, then you break the axiom of the linear space thing, or the partial linear space, right? So you can replace lines and points. And in fact, the second axiom is also sort of dual of itself, because you can look at these 4 lines, right? No 3 of them are concurrent. No 3 of them pass through a common point. So the dual of a projective plane is also a projective plane. What this says in the end is that if you prove any theorem about projective planes, then the dual theorem of that would also be true, where you replace points by lines. Okay, where you exchange this. So this is really crucial. Okay, and what's the main example we will be working with? Well, in fact, we will see that from any affine plane, we can construct a projective plane. And this is a very, very nice and historical construction I think first observed by artists and then formalized by mathematicians. And this is roughly how it goes. Okay. So remember, in an affine plane, we had these parallel classes. So we had this equivalence relation of parallel lines. So say you have one of this parallel class of parallel lines. This could be infinitely many lines also, right? We are not assuming anything about the field. Now you sort of make sure that they meet each other somehow. You artificially make them meet each other. You add an extra point and make sure that all of them are now passing through this point. So each line in this parallel class gets appended by an extra point. And this is known as the point at infinity for this parallel class. So it's somehow, if you are PG again. So wait, oh yeah, that will be my notation. So for affine geometry, I had a notation of AG2 comma F. And for projective geometry, for the projective plane over a field, I will have this notation, and that's what I'm defining right now. Yeah. So I'm defining what a PG2 comma F is. Okay. Yeah. So PG stands for projective geometry. I just like using that notation. So we know what AG2 comma F is, right? And now from this, we are trying to construct a projective plane. So a point line geometry satisfying these axioms in a sort of artificial kind of way, but it has some historical significance. Okay, so roughly what's happening here, the geometric motivation is that when you try to draw two parallel lines in a plane, right, they end up, depending on your perspective, it might look like they're actually meeting each other at infinity, let's say. So, but formally, we are just describing a very formal process for every parallel class. So this for all parallel classes, let's say pi, add an extra, let's say a new point. Let's say P of pi to all lines in pi. And for different parallel classes, we will have different points. So if pi1 is not equal to pi2, then these points are also distinct. We are ensuring that. Okay, so we're adding exactly as many new points as there are parallel classes in your affine plane. Okay, if you want this AG2 comma F thing in mind, then you can think of these having slope M, right? So these are lines with slope M, and corresponding to M, you are adding a different point. But the construction I'm describing here, in fact, works for any affine plane. So any abstract affine plane, from that you can construct an abstract projective plane. Okay, so once you do that, and then you do another tricky thing. So you make a new line at infinity consisting of all of these points. Oh, sorry, P of pi. So all these new points that you added corresponding to the parallel class, you just make a new set and call it L. This set of all of these points. This is my L infinity. This is what I will mean when I say the line at infinity. Okay, so from any affine plane, do this process, and then you can check both of these axioms are satisfied. You've sort of artificially made sure that now any two lines intersect each other, which is clear from two lines which were parallel in the affine plane. But also this L infinity then intersects every line, which was already there, right? And this you can check yourself. It follows from the previous thing, that from the previous non-degeneracy for the affine plane, where you had 3 points not on a line, you can get a fourth point as well, such that no 3 are on a line. All right, so that's how you get a projective plane from any affine plane, right? And if you start with AG2 comma F, then the projective plane that you get is what we call PG2, F. So that's the model you should keep in mind, that the lines were just your familiar y equal to mx plus c, and now you have added a new point to each of those lines at infinity. Let me show you a nice picture for exactly what we did. So this is PG2, 2. Because you observe here that these 4 points, so if you just look at this thing here, this is my AG of 2, 2, my affine plane over F2. You have these 4 lines, these 6 lines, bad at counting. So this is your affine plane. Now for each parallel class, so this was a parallel class, I added a new point. For this parallel class, I added this new point. For this parallel class, I added this extra new point. And then this line is my L infinity, right? And this is known as the Whanau plane, the person who described this construction for the first time, Italian mathematician from 19th century. And I can just give you this example directly, and you can check all the axioms as well, that this is a projective plane. Okay, so I hope that's clear what projective planes are. If you're seeing it for the first time, it could be a bit overwhelming, but we'll get comfortable with them because we'll just keep seeing them all the time in every construction. Okay. Again, just from these axioms, and in fact, now you can use your connection with the affine planes, you can derive a lot of structural information for your projective plane as well. And there's one thing which I should have mentioned before we start reading what this is, that, you can actually reverse this process. The process that I described here, you can reverse it. You can actually start with any projective plane, for example, say this projective plane, and remove your line. Pick any line of the projective plane. Let's say we pick some other one. We pick this line. You remove this line, you remove all the points on this line, and then you actually end up with an affine plane. You can also prove that. Alp is asking, could you repeat which incidences you are adding to the points at infinity? You're just adding, so the point at infinity. So say this is a point at infinity. It's incident to all of these lines in the parallel class that it corresponded to. So this point is defined for each parallel class, there's a point. So it's incident to all of these lines, and it is incident to L infinity. Yeah. Okay. So this process is reversible. You can actually just remove any line from, you pick your favorite line, remove it from the projective plane, you always end up with an affine plane, right? And it is actually theoretically possible, and does happen in some weird cases, that different lines, removal of different lines can give you different affine planes, non-isomorphic affine planes. It will not happen with the examples we will see, so it's okay. But yeah, these crazy things can happen in weird looking planes. All right. So now that we know this bijection between affine planes and projective planes, we can derive the structural information about the order of a projective plane from the information we had for the affine planes. So say you have a projective plane, which is a finite one, and now you take the affine plane corresponding to it by just removing any line. We knew that affine plane had an order n that we proved before, right? And now we just see that in the affine plane, there were n points on each line. So in the projective plane, there will be n plus 1 points on each line. The number of lines through each point, it will require some case analysis because you have this L infinity as well. But you can check that now the number of lines through each point is n plus 1. Or you could use duality. You do know that the dual is also a projective plane, so you can use that as well. You have n squared plus n plus 1 points. In the affine plane, you had these n squared points, and you added n plus 1 new points. These corresponded to the n plus 1 parallel classes. And you have n squared plus n plus 1 lines. Okay. Again, the typical example for a finite projective plane will be denoted by PG2, Q. This is FQ. We are working over the finite field, and that gives me a finite projective plane of order Q. Okay. Any questions for projective planes? Yeah, maybe it was too fast. If not, then okay, I'll move on. Now, here is another model of projective planes. And in fact, it's an equivalent model, but this is another model that maybe some of you are familiar with. If not, it will be really nice to get familiar with this alternate model of the same projective plane, PG2, F. So this projective plane that we just constructed starting from AG2, F over the field F, you can construct a projective plane in another way where you take all the points as one-dimensional vector subspaces. Let me just be very clear. Vector subspaces of this vector space. So take your three-dimensional vector space, f to the 3, and define your point set to be the set of all one-dimensional subspaces. Define your line set as a set of all two-dimensional subspaces. And incidence is just containment. So whenever your one-dimensional subspace is contained in a two-dimensional subspace, we just say that this point is incident to that line. And this is actually the same projective plane, just that it's a different model of the same projective plane. So quickly, let me try to convince you why it's the same projective plane. So look at this f to 3, ag 3, f. I haven't defined it, but you can sort of naturally, you can come up with the definition yourself for what this is. Just take the three-dimensional space f to the 3 and take all lines in that, right? And in this ag3, f, yeah, just think of the real space for now. So say this is the Euclidean three-dimensional space, right? Now look at this z equal to 1 plane over here. From using this, I will show you an isomorphism between this model and the previous model. And here's how it goes. Firstly, for every one-dimensional vector space, which is a line through origin in this model, there's a unique point on the z equal to 1 plane where it intersects this plane, right? So just to be clear, this z equal to 1 thing is isomorphic to ag2, f. And every one-dimensional space intersects this in a unique point, except for these one-dimensional spaces, right? If you take any line which is in the xy plane, so let's say this is x, y, z. If you have a line here, then it won't meet the z equal to 1 plane, but everything else meets it. So all the one-dimensional subspaces not lying in this xy plane, they give you points of ag2, f. And in fact, the subspaces which lie here, they correspond to the lines at infinity meeting. Let me try to just draw it in a nice way. So if you have a line here, and then it just corresponds to, we just artificially say that the point at infinity where all of these lines meet corresponds to this one-dimensional space. Is it roughly clear what the isomorphism would be between the points? Similarly, if you have the two-dimensional subspace of f cubed through the origin, you can take its intersection with z equal to 1. That gives you a line in there. Except for this xy plane, which does not intersect z equal to 1. And this xy plane corresponds to then, xy plane corresponds to L infinity. That's my isomorphism. Okay. So we can just work with any model that we want. And sometimes it's better to work with this model, especially because, yeah, you'll see. Okay, you'll see once I just start talking about it. Okay, so clearly from the notation that I have been using so far, PG2, F and AG2, F, you must have guessed that you can just replace this 2 by n. Right? There must be some higher dimensional analog of these affine spaces and projective spaces. And from this definition, you can very easily just directly define what PG n comma f is. So the n-dimensional projective space over any field f is just a point line geometry, a linear space where the points are one-dimensional subspaces of this n plus one-dimensional vector space, and your lines are two-dimensional subspaces of this n plus one-dimensional vector space. And we can actually carry on your planes and solids and so on till hyperplanes. You can define them yourself. These are three-dimensional subspaces, four-dimensional, and n-dimensional. It's very easy to mistake the dimensions here. Like the vector space dimension is always one higher than the projective dimension. So just remember that. I could have defined an n-dimensional projective space using the axioms, using the abstract way that we saw for projective planes and affine planes, but I did not do that because of this fundamental result in projective geometry from 1910, which says that every abstract projective space, so I'm not telling you the axiom, they will be in the notes, hopefully, but if you define any notion of this natural notion of this abstract projective space, then you can define the notion of a rank there as well. And if your rank or the dimension is at least three, in other words, if it's not a point, a line, or a projective plane, then you can actually show that it's isomorphic to PG n comma f for some division ring f. So it's a field where it's all the axioms of a field, but except for commutativity. And this is a really big, important result. So what it tells you that to study higher dimensional projective spaces, you can just focus on this. You don't need to look at any other crazy examples. All of them will be isomorphic to something like this. Okay. All right, so maybe we take a quick break now, and you can digest this stuff. We'll have a 15-minute, is division ring needed? It is known that fields are not enough. Okay, yeah, so for the infinite case, if your field is infinite, then you get new examples if you take division ring. You don't get the same example. For the finite case, you can show that, well, there's a famous result of Wedderburn that every finite division ring is a field. So in that case, you don't gain anything. But in the infinite case, yeah, this is important. Yeah. Okay. Any other questions before we take a 15-minute break? Any intuition for why characterizing are much easier? So the idea, it's not an intuition, but the way the proof goes is that there's a thing called Desargues' theorem, so which is like a geometric result. And if your dimension of the projective space, of the abstract projective space, is at least 3, you can show that this geometric theorem naturally holds true in your projective space. It's just, and that's an easy argument. Once I tell you what the theorem is and whatever the concepts are, from first principles, you can prove that any projective space of dimension at least 3 must satisfy this thing known as Desargues. And then the work of Veblen and Young was yeah, that's the hard work there, which I have not much intuition about, where they say that once you have Desargues' theorem, then you can actually construct a division ring out of it. You can make a division ring geometrically and prove that your projective space is actually comes from a division ring. And you can do this in the affine in dimension 2 as well. So as long as your theorem, Desargues' theorem, is true, it has to be isomorphic to something like this. But in the projective plane case, this theorem does not follow from the axioms. So you have what we call non-Desarguian projective planes. And yeah, they don't come from PG and GAF. Yeah. But I can't give you an intuition of the proof. You create these weird things. Yeah, you create these ternary rings, I guess, and do something. I don't know. Yeah, I can't give you that much intuition about that. Maybe some geometry people can tell you something. Any other questions? No. So yeah, let's take maybe a 10-minute break now. And in the next half, we will see how this dimension, this description also tells you that we can use coordinates and we can define algebraic objects in projective spaces. And that leads to some very interesting point line geometries later on. Once you start adding coordinates and doing algebra, polynomial equations, varieties, and all that, that gives you a nice combinatorial structures also. That's the plan for the next half. Okay, yeah. Give me a second. Let me adjust the screens. Okay, so this model of the n-dimensional projective space, PG n comma f that we saw, allows us to give coordinates to each point. So each point can be described algebraically, and then you can also look at sets of points satisfying algebraic equations, the so-called projective varieties, if you want to be fancy. Okay, so here's how you give coordinates. So remember that each point of the projective space is a one-dimensional vector subspace of f to the n plus 1. So a vector subspace is spanned by a non-zero vector. So say this is your non-zero vector, then any non-zero multiple of this also spans the vector subspace, right? So all you do is informally, let's say, you can say that whenever you write a coordinate x0 to xn, then any multiple of that, any non-zero multiple of that is also a coordinate of the same point. So for example, 1, 0, 2 is the same thing as 2, 0, 4, if 2 is non-zero, let's say, because 2 would be 0 in finite fields, in some of the finite fields. Okay, so that's what you do. But of course, you can formalize it as saying this thing defines an equivalence relation, and then you can pick some unique representative of the equivalence class, and that could be the coordinate. So you could, for example, left normalize, which means that the first non-zero coordinate from left to right, you could make sure that's equal to 1 by just dividing out by whatever the non-zero coordinate is. Or you could right normalize, and then that can give you a unique representation as well if you want. For example, just so that we get comfortable with this, if you have PG 2, f, the two-dimensional projective plane over the field f, then its point set can be written as, you can say 1 lambda mu, not in your field, union this one, 1 comma lambda, and finally 0 comma 0 comma 1. Yeah. Okay, so these are all the points of PG 2 comma f. F could be the finite field, and then you just write down all of these finitely many points as well. You can think of, just to recall so that you get comfortable with this, these points correspond to z equal to, wait, let's write it like this first. So this could be seen as L infinity, which is defined by the equation x equal to 0. So you can think of these points, the first set of points, as your affine points, your AG2 comma f, right? Because you have lambda comma mu, this one is fixed. And these could be seen as the points at infinity, right? So this is your line at infinity consisting of all of these points. This point here could be seen as z equal to lambda y plus c. So you take in your affine plane, the yz affine plane. So say these coordinates are x, y, z. In your yz plane, which you get by removing x equal to 0, if you have this line, then of slope lambda, then it corresponds to this point in the projective plane, right? And this point corresponds then to all the vertical lines, or y equal to constant lines. Okay, and just to get you comfortable with these coordinates. All right, so whenever you have coordinates, say in the affine space or the projective space for us, you can define what is known as a degree D hypersurface in your n-dimensional projective space as just the set of points which satisfy a degree D polynomial equation, like a single polynomial equation. And for this to make sense, we also assume that your polynomial f of degree D is homogeneous, which means, for example, let's just say that f is equal to x naught square plus x1, x2 plus x3, x4. It's a polynomial, a homogeneous polynomial in general is a degree D polynomial where each monomial has the same degree, the degree D. So this is an example for D equal to 2, right? And the reason why we do this is as follows. For any homogeneous polynomial, you can see that f of lambda times x, say the vector, is equal to 0, well, is equal to lambda to the d f of x. If you have a homogeneous polynomial, this lambda, you can just lambda to the d, you can take out from each monomial, which means that this is 0 implies that this is 0. So if you have a vector, an affine point, let's say, or let's not say affine point, a vector satisfying this equation, then it also, any scalar multiple of that vector also satisfies the equation. So this unambiguously then assigns a point of the projective space, so a one-dimensional space, to the 0 set of your polynomial f. Right? Is that clear? Okay. So this is how you defined these algebraically interesting points in your projective space. And for example, lines are in PG 2, f are degree 1 hypersurfaces. Because you can just define them by something like ax plus by plus cz equal to 0, right? Where not all of these are 0. In general, your hyperplanes or the codimension 1 spaces would be degree 1 hypersurfaces. But of course, these are not the only examples we'll care about. What we are really interested in for now is degree 2 hypersurfaces. They will reappear much later in the course because we really understand degree 2 hypersurfaces quite well. And they give you interesting geometries, which you can use in combinatorics or wherever. For now, let's focus on degree 2 hypersurfaces in the two-dimensional case, so in the projective plane. These are known as conics. For example, you could have x square plus y square plus z square equal to 0. So all the points satisfying this equation. You could have z square minus xy equal to 0. You could also have x plus y plus z square equal to 0. So a line is also a conic by this definition, right? And in fact, you can show, and I leave this to you because it's an easy algebraic manipulation, that if you have any degree 2 hypersurface in PG2, f, in general also, and you take any line L, then either that line is completely contained in the conic or it intersects it in at most 2 points. It will be actually nice to prove this, to get comfortable with projective coordinates and stuff. One thing that might help is if you have a point here in a line, then any arbitrary point here can be seen as x plus lambda y. So say you have y, this could be x plus lambda y, and then you plug it in and then you manipulate and you do something. But try to do it if you have never done projective geometry in your life. Okay, it will help. Yeah, so this is a nice property, but the kind of conics we will be interested in will not contain any lines. We don't want these sort of degenerate conics. We really want something that looks like a conic, or maybe I can, yeah, okay, which really looks like a conic. Okay, and these are known as absolutely irreducible. I'll ignore the term absolutely for now. But a conic C, so a degree 2 hypersurface in PG2, f is called irreducible if the polynomial f that defines it does not factorize into linear factors over any extension of the field f. Okay. In fact, so irreducible is over f, absolutely irreducible is over all extensions. And here's a lemma, which again, I will not prove, but maybe in the notes, there is a proof of this, which says that if you have an irreducible conic, then it definitely does not contain any lines. So these are really non-degenerate objects. And these are very classical objects in mathematics. They have been well studied. I could develop the theory for you and prove the following interesting claim, but we are just going to use them as objects we know to construct some nice graphs and geometries and so on. So here's a classification, which I hope is correct, but I think it is. It says that any irreducible conic in PG2, f can be written as follows, is equivalent to this, in the sense that the cardinality of a degree D hypersurface. Oh yes, and we will definitely say something about that. Thanks. So that's next slide.
Were you comfortable in here, baby, when you're teaching, or you prefer next door?
Sorry?
You prefer here?
Because next door is...
Oh, someone just unmuted themselves, I guess. Okay, yeah. So I will talk about the cardinalities, and they will be crucial throughout the course. I'll keep talking about them later on as well. Okay, so, but over the infinite field, of course, it's infinite. So all irreducible conics turn out to be equivalent to this one over here in PG2, f via some change of basis. So you can change the basis and scale things, and then you can always rewrite the equation as follows. So that's really nice. We really, really understand conics in PG2, f, irreducible conics. Well, the reducible ones are also easy to understand. And once you have this, so say if you believe this theorem, then I can answer the question of Abhishek, the cardinality. So say, okay, so we can say in PG2, Q, we can find out how many points does a conic have. So for those of you who don't know this, do you want to calculate the number of points? So the number of solutions of this equation over FQ, projective solutions. So we are looking for the number of points in the projective plane. Yeah. You can calculate for now. Yeah, we have time. Any guesses or any calculations? Uh, 2q squared. That's a bit too much because the number of points in the projective plane is q squared plus q plus 1. So that's more than the number of points in the projective plane, right? So we are looking for solutions, so projective points. We're not just looking at all solutions, x, y, z, but you also, yeah, so if, for example, let's say, yeah, 1,0, well, this is a bad example, is a solution, then all scalar multiples of it are also solutions, right?
Could you
yeah.
could you sort of
I guess, project onto the line at infinity, say z equals 0,
Yes,
find
yeah.
one solution that way,
Yeah.
and then project onto z equals 1 and look for solutions there?
Yeah, well, projecting into z equal to 1.
Sorry.
Yeah, so you just look at the solutions outside, the affine solutions. So z equal to 1, yeah, exactly. So z equal to 1 will be y square minus x equal to 0. Yeah, exactly. Q plus 1 is the right answer, Alexander. And you could just play around with it, pick any value of y. Yeah, it's a square, so maybe it's a bit tricky here. But you can do this. And Q plus 1 is the correct answer. I could have proved it without using this classification as well. And in fact, in the lecture notes, you'll see some sort of a proof there. But I can give you a rough idea of how that is done. Firstly, you prove something.
Oh, can I ask, sorry?
Yeah, sure.
Is it a coincidence that q plus 1 is the number of points on a projective line? Well, I think of it as that number. Which is a circle, kind of.
Yeah, it's not a coincidence, I
Okay.
believe. But yeah, so roughly your degree, your hypersurfaces will have the same number of points as your hyperplane, but roughly. Here in the 2-dimension case, it so happens that this degree 2 thing has the same number of points. But if you look at degree 2 hypersurfaces in higher dimensions, and we will look at them, then it won't be the case that it's the same number of points as on a hyperplane. But maybe someone who's more familiar can give you a nicer answer in the chat of why it's exactly q plus 1. Yeah, but here's an argument which is roughly from the lecture notes. This is the argument. You can show that for any absolutely irreducible conic, if you take any point on this conic or on this hypersurface, then there exists a unique tangent line. So a unique line through that point which meets this conic in exactly one point, this point itself. Okay, but now once you have proved that, yeah, yeah. So yeah, so now we're working in PG2, Q. You just look at all the other lines passing through this point. So if you take any other line, say this line, then it will meet the conic in exactly one other point, because irreducible conics, you can prove they don't contain any lines. And we saw that there are exactly q plus 1 lines through any point in total, right? And so you get these q other lines, so you get these q distinct points, and then this is the q plus 1th point. That's also a nice argument to keep in mind. Okay. But of course, it requires, I'm skipping a lot of things. Small comment. At least 1 point. Ooh, yes. Very good point. Yeah. But for, wait, I'm reducing it to y square minus zx, right? So that always has a point over any field. So it's okay. I think if you're using some other form, then you need that. There's always at least 1 point. Yeah. Yeah, yeah, exactly. But I'm saying irreducible. Okay, I get your point. Yeah, thanks. Yeah, because I'm using irreducible conics as a very general thing. Yeah. Okay, maybe it's best so that I don't make this mistake. We are working over FQ here, though it works over many other fields as well. And yeah, in the lecture notes, maybe I sketch it that why any degree 2 hypersurface will always contain at least 1 point over the finite fields. It follows from Chevalier-Whanau theorem. So if you know what that is, then that's a very nice, easy way, and then you can do it. Okay, thanks. I'll correct that. All right, so there are these objects. We really understand them. They're useful because one of the reasons why they're useful in finite geometry is because these objects form some sort of an extremal structure to a very natural extremal problem. Okay, so say you are working now in any projective plane of order Q. I'm writing Q because all the known projective planes have order prime power, but really this is not just for PG2, Q, but for all projective planes, right? So say we have any projective plane of order Q, and you take a set of points, a finite projective plane, and you take a set of points such that no 3 points are collinear in that set of points. Then we can show that this set must have cardinality at most q plus 2. and this is the argument. You take one of these points from the set, and now you have these q plus 1 lines through this point, and each of them can have at most one other point of your set. So you have at most q plus 2. But very interestingly, if q is odd, or well, if q is odd, I'm writing the negation of that here, but if q is odd, then you can't have equality here. You can't actually have a set of q plus 2 points, no 3 collinear. So you can only have up to q plus 1 points for q odd, which are such that no 3 of them are collinear. And here is the rough sketch of the argument here. So say q is even, and you have such a set, so say q is odd. Let me think. So say q is odd, and you have such a set of q plus 2 points, and you take a point outside, then you can show that all lines through this point either meet this set in exactly 2 points or 0 points. And the reason for that is if you had a line which was, let's say, tangent, then from this point, you could count the cardinality of your set, and it will be only q plus 1, right? It's the same thing which we are doing here. If you had a tangent line through some point, then there are only q other lines, so there are at most q other points on this set, except for this one. So there won't be any tangent lines, and this then shows that you have a partition, right, into pairs. So this shows that this thing has cardinality even, right? But q plus 2, if q is odd, then q plus 2 is also odd. That's roughly the argument. Okay. And most interestingly, so conics definitely, if you take an irreducible conic, you get an example of size q plus 1 in for any pg2 comma q odd. But there is a beautiful result of Segre from 1955, which I will not prove, but this is in fact seen as it can be seen as an argument using the so-called polynomial method, which shows that if you take any set of q plus 1 points, no 3 collinear, in pg2 comma q, and q is assumed to be odd, then it must come from a conic, from an irreducible conic. You can't have any other crazy examples. So not just these are extremal examples, but these are all the extremal examples out there. Okay, so the set of q plus 1 points in any projective plane of order q, no 3 collinear, is known as an oval, and a set of q plus 2 points, no 3 collinear, is known as a hyperoval. That's just a terminology for you. Ovals, what Segre's theorem says is that ovals in order q, Desagian or classical projective planes, they have to come from an irreducible conic. Hyperovals, we don't know. And in fact, there will be a nice exercise around ovals and hyperovals, but let me just give you an example of a hyperoval. So these objects do exist when q is even. And here is a quick example. Just take all of these points and I guess you take 1, 0. Yeah. So take these q points and 2 more, and if q is even, which means it's a power of 2 in here because it's a field, then you can show that this set has the property that no 3 points are collinear. So these objects do exist, but there are many, many, many more crazy examples, many of them named after suburbs in Australia because some Australian mathematicians discovered them. I think there was some Subiaco hyperoval named after a district in Perth where I was living until recently. Okay. So
Was that by
this-
Michael Giudice?
That's by Tim Pentilla and some co-authors. Michael Giudice was a student back then, I think,
Okay.
undergrad student back then. Yeah.
I used to
yeah,
live near Subiaco as well.
yeah, so it's named after not just the district. In fact, there's a cricket stadium, so which is called an oval. So in Subiaco, there's a cricket stadium, and we named
Oh,
it
yes.
after that Subiaco oval, hyper oval. Okay. So there are examples. There are many more examples. You'll prove some properties of hyperovals and ovals in the exercises. But it's good to know that for any even Q, we can construct these objects. So there is this easy construction. Why this does not work, why this construction does not work, you can check just algebraically. You will find a line, 3 points on a line. But the argument which I was sketching here, let me just do that again. So for Q odd, so say, let's just write it. Say Q is odd, and you have a set of Q plus 2 points, no 3 collinear, then you just take any point in the projective plane outside it and look at all the lines through this point. You show that there can't be any line, this is not possible. There can't be any line that meets this set in exactly 1 point. So every line, each of these lines meet in 2 or 0 points. This means that this set must have even cardinality. But if Q is odd, then Q plus 2 is also odd. Is that clear? Quick sketch. But in the lecture notes, you'll see a proper thing. Yeah, okay. Good. So we are done with this part. And now we get to the more interesting and sort of unusual things that even if you did know about finite geometry, you might not have known about these interesting finite geometries, because projective planes and affine planes, almost everyone at least sees them somewhere. But we move on to the next interesting example. Wait, how much time do I have? 20 minutes, I guess. 15, 20. Okay. Okay, so this is a point line geometry, a partial linear space that we'll introduce now, which will be really, really crucial for all the Ramsay theory applications that we will see later. If you do know Ramsay theory, then you would know about things like triangle-free graphs, and when you want to construct certain triangle-free graphs with whatever properties, and generalized quadrangles actually give you a lot of those examples. So they are point line geometries which are in some sense triangle-free, okay, in a very vague way. If you come from finite geometry, then you already know why these are very important. These are very interesting algebraic objects. They give you nice groups. For example, finite simple groups, many of them, they come from generalized quadrangles as well. So these are very nice algebraic important objects, but for combinatorics, especially Ramsay theory, we will be using them. And as before, we'll define a partial linear space. So this point line geometry, finally, it's not a linear space, it's a proper partial linear space, which has just these two axioms, which I drew a picture. And the axioms are as follows. Okay, so the first axiom says that if you take any line L and any point not on L, so not incident to L, then there exists a unique line through X that meets L. So there exists a unique, there exists a unique M. So let's say this was M, such that X is incident to M and M intersection L is non-empty. So sort of geometrically, what I was saying before, you can't have a situation like this. You can't have a triangle, let's say, right? Because then through this point, there are two lines. There are two possibilities for M which meet L. That's the main axiom. And as before, there's a non-degeneracy thing, which I don't know, depending on your taste, you might want a stronger non-degeneracy thing, but for now, this is okay. That through each point, there are at least two lines. Now remember, when I was defining a partial linear space, In the definition, I had this condition that every line is incident to at least 2 points. So this is the dual statement of that. Through every point, there are at least 2 lines. And again, from these axioms, you can actually check that this is again a dual, a structure that has some duality. Just like projective planes, if you replace points with lines and lines with points, then you can check that these 2 axioms are again satisfied. So the dual of a generalized quadrangle, I'll just call them GQs, is also a generalized quadrangle. You should try to prove it yourself. It helps to play around with the axioms. Let's just give some examples. The easiest example, let's say, is a grid. So here, these are my lines, the 3 horizontal lines, and let's say the 4 vertical lines, and I have these intersection points as my points. Okay, and then you can check firstly through each point there are exactly 2 lines, one horizontal, one vertical, so this is fine. The second axiom, and for the first one, yeah, just case analysis maybe, but if you take this, for example, then this thing is the, oh no, sorry, my bad. This is not an affine plane. If you take this, then this thing is the unique line M. All right. So grids are definitely generalized quadrangles. And I just told you that the dual of a generalized quadrangle is also a generalized quadrangle. Can you quickly tell me what the dual of this, if you replace points with lines, what does it look like? It's something you all are familiar with. It's, yeah. Any ideas? I'll just wait for the chat to give some answer. I'll just give a hint. It's a graph. Exactly. So it's in fact K3, 4 here. It's the graph, the bipartite graph. Let's say these are my 3 horizontal lines, and so these are my 3 horizontal lines, these are my 4 vertical lines, and then they pairwise meet. So this complete bipartite graph, whatever, all the possible connections. So complete bipartite graphs are also generalized quadrangles. Very trivial sort of generalized quadrangles, just like I will call grids to be trivial generalized quadrangles, and we will see what this trivial means. The first non-trivial example, which I find extremely beautiful, is the so-called doily, which is drawn here. Okay. These curvy things are lines. So this is a line with 3 points. This is also a line with 3 points, and then these are the lines. And I can just give you the picture and you can do a case analysis, or you can just convince yourself that both the axioms are satisfied. But we will see a construction of this. We will see, in fact, an infinite family, well, maybe a couple of infinite families for which this is the base example. But it's good to note that there are these non-degenerate, but I will define what non-degenerate is. And you can already maybe guess the non-degeneracy here is that through every point, there are more than, strictly more than 2 lines. In fact, there are exactly 3 lines. And on each line, there are exactly 3 points also. If you take the dual of this, then you actually get the same thing. So it's self-dual. It's isomorphic to its dual. And this incident structure, because I like it so much, I'll mention it's already due to Sylvester from 1861. Of course, there was no notion of generalized quadrangles or whatever, but this object has existed since then. And in fact, it is related to the symmetric group S6, the symmetric group on 6 elements. You can use this nice object to show that S6 has an outer automorphism, if you know what those things are. And in fact, this is the only symmetric group that has an outer automorphism. There's a really beautiful proof of that using the doily. Okay, so this thing has existed for a long time. I think the picture is much later by Stanley Payne, who called it doily because it looks like a doily, if you know what doilies are. Okay, so there are some non-degenerate examples. We will see an infinite family, a nice construction. But before that, we can maybe Stan Payne in 1973. Yeah. Okay, before that, let's just try to prove again some structural properties of generalized quadrangles. And these examples here, this already tells you that unlike the case of projective planes, we can't expect an order n in the sense that every line has a constant number of points and through every point there's the same number of lines, right? These two, or in fact, even every line having a constant number of points is not the case because these lines have 4 points, these lines have 3 points. So we can't really expect that, but there is still structure. So a GQ is known to have order s comma t. So this is what I'm talking about. If every line has s plus 1 points, and through every point there are t plus 1 lines. We do the plus 1 thing for convenience because in the examples, s and t would be like prime powers. So you have prime power plus 1. And here's the structural result, which says that if a generalized quadrangle has 2 points on each line. So if every line has exactly 2 points, then you can just show that it is the complete bipartite graph for some KNM. Again, if you're seeing it for the first time, use the axiom and prove that if every line has exactly 2 points, so it's a graph satisfying these axioms, then it is the complete bipartite graph. And then dually also you can check that if through every point there is exactly 2 lines, then it has to be the grid. It has to be the other example. If we assume that the generalized quadrangle is neither of these two trivial examples, then we can prove that it has an order. So here's our first theorem for generalized quadrangles, that every generalized quadrangle which is not a grid or its dual has an order s comma t. Okay? So there are these constants. Okay, and let me prove that to you before we move on. So here's a quick proof. So let's assume it's not the dual grid. So it's not a complete bipartite graph. So there has to exist at least one line. There has to exist at least one line with at least 3 points on it, right? Because if every line has 2 points, then it's just the dual grid. Now through, let's say these points are u, v, w. Through this point, there are at least 2 lines. Take another one and just take any point z on that. Okay, so just this picture, how I've drawn it. Now you can show that the number of lines through z, let me denote that by t sub z plus 1, we'll have t plus 1 in the end, is equal to tv plus 1, which is also equal to tu plus 1. So I can actually give you a bijection between all the lines through z and all the lines through v. Okay, and here's the bijection. Firstly, note that these are non-collinear. So there is no line passing through both v and z, because if there was a line, then this will break the axiom of the GQ. You will have this triangle. So there is no such line. Now, if you take any line through z, then through v, there's a unique line meeting this line in some point by the first axiom. It's the same sort of a thing we were doing with affine planes before. And this can then be used to show a bijection between this, the set of lines through z and the set of lines through v. Okay, so once we have that, we can just take a line through u and some point here like y to show that the number of lines through y is the same as number of lines through v and w. So you also get that tv plus 1 is t sub w plus 1. In particular, you see that through all of these points on L, there is a constant t number of t plus 1 number of lines, right, by just repeating this argument. So we do know that there is a constant t, which denotes the number of lines through each point on L. But if you take a point outside L, so now we know L, and we take any point outside L, there must be some point here, because there's a unique line, there must be some point here. So for each x, there must be an x prime such that they are not collinear. There is no line passing through them. So the number of lines through x should also be equal to the number of lines through x prime. Right? So every point on the line has the same degree, let's say, or the same order, and every point outside the line also has the same, exactly the same order. All right, so this shows the existence of the constant t. And now you can just dualize, use the duality here in the axioms to prove the same thing for S, the existence of S. You can just dualize the argument also, replace lines by points and points by lines, and then you get the argument. So every generalized quadrangle, which is not a grid or a dual grid, has an order S comma T. Okay. Now, before we end, I would like to give you at least one nice infinite family, one nice example to remember, which requires the least amount of theory. This is the example I could find that does not require all the other crazy things we'll be doing in 2 or 3 lectures from now. All you need is the projective plane, the definition of a projective space, and the definition of a hyperoval. And using that, you can define a nice infinite family of generalized quadrangles. So here's the construction. This will be the last thing. Say we are in PG 3, Q, 3-dimensional projective space. And we take a plane pi, which is of course then isomorphic to take any plane in your 3-dimensional projective space. And now take a hyperoval inside this plane. So we assume Q even. As I said, hyperovals only exist for even order projective planes. So say you have a hyperoval inside this plane. So a set of Q plus 2 points, no 3 collinear. Okay, now here is my generalized quadrangle. My points are all affine points. That is all the points outside this hyperplane, or this, sorry, outside this plane. So every point inside PG3, Q, which does not lie on pi, will be a point of my generalized quadrangle. Okay. And my lines are all lines, again, outside pi. So no line contained in the plane, but every line which is outside that meet pi in the hyperoval. So only these kind of lines. So this is not there, this is there. So geometrically, you can visualize this, that you have this hyperplane at infinity, which corresponds to the directions of your lines. And you are forbidding, you're making sure that you take lines only in certain directions, so that the directions form a hyperoval inside your PG 2, Q. Then this is a generalized quadrangle. That's my claim, that this is a generalized quadrangle of order, let's say, what should be the order? Maybe you can guess what the order would be. How many points are there on each line? Quickly, if someone can type. Q. So there are Q points on each line, hence the order, the S thing is Q minus 1. We take this S plus 1 business, whatever. And then you can check that through each point, there are indeed Q plus 2 lines. So this will be Q plus 1. You can check outside. If you take a point, then there are, for each of the point here, there's a unique line joining them. So these are the Q plus 2 lines from that. And then you can just use basic geometry, and you will see the proof in the lecture notes. Really easy argument to show that the axioms of the generalized quadrangle are satisfied. Okay, so this has q square points and a certain number of lines which I'll have to calculate. So maybe I can q plus 2, because I'm cheating, that's why I can calculate, multiplied by q cubed points. Sorry, it has q cubed points and I believe these many lines. So we have an infinite family of generalized quadrangles which you can use for all sorts of things. And I will, before coming to more geometric examples, you will see something in the exercise maybe, but like we will go to the theory after a few lectures. But before that, I'll actually apply this generalized quadrangle to a Ramsey theory problem. I'll use this to give you really nice constructions for Ramsey theory. And let me just quickly mention that this example is by Arons and Sekeresh. This is the same guy from Erdős-Sekeresh theorem from Ramsey theory. When he was in Australia, I guess he was doing some finite geometry, I guess. And they gave this example. They gave an example for odd Q as well. It's more difficult to describe, but for Q even it's really easy. And their motivation, I think, except for constructing new generalized quadrangles, was also to understand, no, definitely not. GQSTs are all over the place. There is no classification, no whatever, yeah. But their motivation for this construction, it's a nice fact, came from this algebraic geometry thing. Wait, let me mention it somewhere. 27 lines on a cubic surface. If you know this fact from algebraic geometry, that a smooth cubic surface, I think in PG3Q, I guess, has exactly 27 lines, say over the real phase field, I guess. Maybe Wouter can correct me with all the facts from algebraic geometry, but there is this well-known thing for 27 lines on a cubic surface. And if you just look at the incidences between these lines, you get a generalized quadrangle. In fact, you get one of these examples. So they sort of generalize that example to come up with this construction. But this is the easiest construction I know that I can just describe right away. For other constructions, you will have to wait till the end of this week where we develop some more theory. But in the next lecture, I'll prove some graph theoretical things, some basic concepts from spectral graph theory. And then in the lecture after that, we will start seeing applications in Ramsey theory. So that's the plan. Okay, so I think I should end now. If you have any questions, just ask. Unmute yourself or type in the chat. Yeah. I'll stop the recording now.